Okay, so Jim's going to say something before I talk about motivic Galois groups.
That's right. So I just want to give a slight preamble here to describe the attitude that I tend to take when listening to stuff about motives. And it's perhaps not that different from the attitude that everyone takes when listening to stuff about everything. But I just want to say it out loud anyway. So I know, more or less by rumor, that motives are supposed to be really related to stuff that I'm really interested in. But I really don't understand them yet. I don't understand how to really fit them into, I don't understand how to really fit them in with the stories and pictures that I do understand. And therefore, my attitude when listening to this stuff is that I'm very interested, but also skeptical. And also that I'm undecided about how many or how deep questions I should be asking, including the possibility that, maybe I should mostly just listen and then think about it. And then later, after I get a chance to think about it, ask most of my questions. So I just wanted to say that before we started. And now I'm ready.
Okay. So once upon a time, we had a chat where I went through the definition or definitions of motives.
Right.
I don't really want to do that again. And
right.
So but also I don't mostly expect you to need to know that for this. So this is sort of like some cool stuff people do with motives that maybe will make us more interested in motives or something like that.
Okay.
Okay, let's see if I can get this screen thing to work. Okay, so this is a talk by a guy named Bruno Kahn.
Okay.
So the basic idea is that if you do things right, motives form a category that by abstract nonsense you can show as the category of representations of some group, and that group is called a motivic Galois group. So he starts out with the abstract nonsense, which is of Tanakian categories. And I don't even necessarily want to get into this particularly.
Well, can I just make one quick comment about it? That I'm always throwing around the word Tanakian, so that raises questions of what's the relationship between his usage of Tanakian and my usage of Tanakian, and we're not going to settle that right now because I use it in a very generalized way. But go ahead.
So I'll just say this much: that there's this Tanaka theorem that you have a category that's nice enough with a functor to the category of vector spaces that's nice enough, then the endomorphisms of that forgetful functor form a group. And if everything is nice enough, then you show that your category here called A is the equivalent to the category of representations of that group. Now, there are lots of variants of that scheme setup.
Sure.
And so I don't want to get into all of them, but here he's doing algebraic geometry. So he's being a little bit fancy. So he's working over a field. And to make things even more confusing, he's not assuming that field is algebraically closed. So he's got like another field L that's bigger. And so the field, so this forgetful functor is going to vector spaces over this bigger field. I don't really care about any of that. But maybe what I care about a little bit is that the kind of group you get from this Tanaka construction is going to be an affine group scheme. So it's in the world of algebraic geometry. And these representations are going to be the kind of representations that you expect of affine group schemes.
Yes, it looks very plausible so far. Go ahead, yes.
So that last part, I mean, that's supposed to be good, right? Because we sort of like stuff like that.
Yes.
I will avoid, there's all sorts of things one could talk about. I'll just raise one question, which I don't want you to answer now.
Okay.
But I want you to answer sometime. which
Okay.
is that you like doctrines that are heavy on colimits, but not mixing limits and colimits. Whereas
Right.
this typical Tanakian setup assumes you've got an abelian category.
Right. Right.
So one thing I just want to know, but not now,
Right.
but I really do want to know it, but not now, is it like, what are the kinds of Tanakian reconstruction theorems that you can do in the more colimit, only colimit approach? I think that
Yeah.
would be.
Yes, those are very interesting questions. They're very open-ended. Yes.
Okay, so anyway, well, anyway, this theorem due to, I don't care about it, but there's this theorem due to Grothendieck and Saavedra, which says when the Tanaka reconstruction actually works under some conditions, you get an equivalence of categories between your original category and representations of this group. I guess one thing that's I mean, so I don't want to get into it, but one thing that's more interesting to me, just because it's sort of newer to me, is that then you can show that this category is semi-simple if and only if the group is something like reductive, but actually pro-reductive. So I guess there's pro stuff going on here. So that I would like to understand better sometime. I don't want to, there's lots of interesting things here, but most of them I don't want to.
Sure.
So one thing is that when we define motives, it's sort of a several step process. And one step of the process is we think about correspondences between algebraic varieties. And they're like spans, but the apex of the span, I mean, there's with some properties, and the apex of the span has an algebraic cycle in it. So they're sort of like spans weighted by an algebraic cycle. But to get this stuff to work, you use an equivalence relation on algebraic cycles to simplify things and make things work. And so there's this whole yoga, which we've talked about, about what kind of equivalence relation you want to use.
Yes.
And the coarsest one is the coarsest so-called adequate equivalence relation is numerical equivalence.
Yes.
Just like about intersection numbers.
Yes.
And there's a nice fact, which probably will come up later, which is that when you use numerical equivalence, you get a Tanakian category. And then and the same guy who proved that, a guy named Jansen, proved that if you use any equivalence relation other than numerical equivalence, you don't get a Tanakian category. And part of why that's interesting is that Grothendieck didn't want to use numerical equivalence, really. He really wanted to use something he called homological equivalence.
Yes.
It's equivalence with respect to homology of these algebraic cycles, where the homology could be any so-called Vect homology theory.
Yes.
But one of Grothendieck's conjectures, standard conjectures, was that equivalence relation is the same as numerical equivalence. And he could only have pushed ahead his proof of the Vect conjectures using the setup if he were able to prove that. And nobody was ever able to prove that.
Or disprove it, or
disprove it, yeah.
Or disprove it, okay.
Right. So we're in this funny situation where we know the category of motives is pretty good for numerical equivalence. So like if you want to actually work with a Tanakian category, then that's what you have to use. But if you want all of Grothendieck's dreams to hold, then you have to hope that numerical equivalence is also some other superficially finer equivalence relation. But anyway, if you're just interested in getting a Tanakian category, you use numerical equivalence. Then there's this like annoying technical point. Well, it's just annoying because people don't like come right out and say how minor it is. That if you that in fact, well, I mean, here he's like making it sound like really bad. This category of motives with numerical equivalence is never Tanakian. But the reason why is just because as there are two different symmetries you can put on this symmetric monoidal category, one of which sticks in minus signs when you braid to odd things like odd dimension cycles.
Yes.
And one in which you don't. And the sort of the default one has the minus signs in it. And that would give you what I might call like a super Tanakian category.
Yes.
And so if you want a Tanakian category, you have to not put the minus signs in it. And so that's what so here they're saying like, it's never Tanakian because the dimensions of things can come out to be negative. Well, that's exactly, you get Euler characteristics as dimensions of varieties. That is, a variety gives you a motive, and then you can like work out its dimension in a very category theoretic way in any Tanakian category.
Yeah, from my very limited perspective, I might suspect that super Tanakian might actually be better than Tanakian, but I have no idea. No idea.
Well, I think it actually is. I'm pretty sure. Yeah, I'm pretty sure it's basically better. You just need to sort of put Z2 grading in more of your concepts to work with it. So anyway, but it's for us anyway. Again, that's something I don't really want to talk about, but I
sure.
Anyway, I'm talking about it just because like at first I kept reading like it's not Tanakian. You have to do something to it to make it Tanakian, and then they made it sound as if it was like some more scary thing you had to deal with, and it actually is. So okay, so yeah, so Janssen is the one who like, don't ignore most of this junk. There are all these standard conjectures and implications between them. But Janssen was the guy who proved a really good thing, which is, I said it wrong. For finite, sounds weaker than what I said. For finite fields, you get a Tanakian category of motives.
That's okay. And I think you might have said something like that last time, but I don't remember.
For some reason, I was hoping it was like for more.
Yeah, I don't remember.
So this suitable modification is just this business about switching the braiding. Then there's something that's like a little more interesting because it's like it gets into some more juicy stuff. For me, I'm interested in like getting a feeling for things rather than all the technical details. So one thing that you can do is you can take some subcategory of motives, which is also Tanakian. So I don't even know what a thick subcategory is, but rigid means like the duals are in there. So if you take a good enough subcategory, it gives you its own group. That'll be a quotient of the full-fledged group. I guess you can sort of imagine that, Jim. Probably that's not weird for you. So that can be nice because then sometimes these quotients of the motivic Galois group are more tractable and to sort of shed light on the whole thing.
So far you haven't, as far as I know, you haven't, nothing you've said so far particularly sounds like these motivic Galois groups are going to be pro-reductive or reductive or something like that. But I shouldn't even worry about that. I'm just idly curious. Go ahead.
Yep. So one thing that you can do that's nice is you just take a particular variety X, turn it into a motive, that's called
Yes.
H, and you let it generate a Tanakian subcategory.
Well, that's very suggestive for various reasons I won't get into now. Go ahead, yeah.
And so then that will give you a group by Tanaka reconstruction. And so they call that the motivic Galois group of the particular variety.
Well, I just can't resist saying one thing, which is when you have one of these representation categories and you take the sub nice thing generated by that, you tend to get the quotient group that that representation sees. So if that's a very faithful representation, you'll get a mild quotient. But if it's a very unfaithful representation, then you'll get a very coarse quotient of the Galois group.
Yeah, that's exactly. Yeah, that's exactly the type of thing that's going on. here. So they could do it either for a single object or for like a bunch of objects. And it's very,
I mean, there's a bunch of interesting things about that, but go ahead. Yeah.
yeah, well, there's going to be some examples, which is what I'm trying to
Okay.
lead up to. So here are some, like, so Artin motives are really the motives, as far as I know, they're the motives generated by zero-dimensional scheme. But those are, if I'm not mistaken, I guess they're like co-products of schemes that just come from fields, field extensions, finite,
something like that. Yeah.
Finite dimensional field extensions.
Yeah.
So if you look at just those motives, the Artin motives, and you look at the motivic Galois group that you get from them, from that subcategory, then that gives you the Galois group of your field, of your original field.
The representations, the Galois representations, yes. And that sort of seems to motivate the terminology motivic Galois group.
Yeah, that's right. Maybe I'll jump ahead, and there's like some, if you assume a bunch of these conjectures, Hodge, Tate conjectures, standard conjectures, blah, blah, blah. Sorry, there's like lots of conjectures. Then, so like if you assume all the conjectures that you want,
yeah,
then you get this short exact sequence. So this is the motivic Galois group of K. This is just the Galois group of K.
Yes.
And then this is the motivic Galois group of the algebraic completion of K.
That's interesting. Okay, yeah, that makes some sense. Yeah.
And so they're reminding us that G sub K, Galois group of K, corresponds to motives of zero-dimensional varieties, aka Artin motives.
I mean, I can imagine some people getting more interested in that thing on the left than the thing on the middle, in the middle.
Yeah, well, that's sort of, yeah. Well, especially because if you're a number theorist, you're supposed to sort of understand the thing on the right already.
Well, but right, there could also be people who are really interested in the middle and how the left and the right interact in the middle. Yeah. Yes, okay.
And here they're adding something which is not obvious at all to me, which is that the group on the left is connected. That actually winds up being one reason why people start thinking about Lie algebras.
Right.
Situation.
Right. Yeah, that's interesting. That's interesting.
So this is sort of, yeah, so this is sort of good to know, I think, that so motivic Galois groups are sort of a blend of plain old Galois groups and then like this new interesting stuff that you already for algebraically closed fields. That's higher dimensional aspects of what's going on. And then going back to like another thing I wanted to point out, like another example of, well, I feel like a couple of other examples I want to mention of like how you simplify the motivic Galois group.
Yeah.
So there's this particular motive called the Lefschetz motive, which is like the motive for the projective line,
right?
Sort of subtract off a summand, which is the motive for the point.
Right. We've talked a little bit about that. Go ahead. Yeah.
Yeah. So just to remind our
some motivations behind it. Yeah. Go ahead.
Yeah. Just to remind our audience, when part of the process of constructing the category of motives, sort of like the last step is to throw in a dual or in fact inverse of this Lefschetz motive. It's called the Tate motive.
Yes.
So if you take the Lefschetz motive and then you generate one of these Tanakian subcategories, starting just from it, you're going to throw in its inverse, which is the so-called Tate motive, and then other stuff, tensor products of those and direct sums or co-products of those and stuff. So you get this sort of pretty tame bunch of motives in some sense. I think it's pretty tame. And and its motivic Galois group is just the multiplicative group.
The multiplicative group. Okay, that's
Yes.
interesting.
So
I mean,
guess-
I'm not sure what to make of it yet, but that's very interesting. Yeah, go ahead.
I guess it has something to do with how symmetries of the line are the multiplicative group. Automorphisms of a line are a multiplicative group.
Yeah. Well,
So that's like another,
some symmetries of the line, yeah.
oh, yeah, of the, yep, you're right, just some, yeah, that's true.
Enough, not enough points marked, yeah.
Yeah, yep. Yeah, so I don't really understand it, but it sounds nice.
Uh-huh.
And then we'll sometimes put both the Artin and the Tate motive in there together, and then you just get a direct product of those two.
Uh-huh.
You could throw in just an elliptic curve, but I haven't thought about that yet, so I don't want to think about that.
Well, could be interesting, but go ahead, yeah.
Yeah, it's probably extremely interesting, but I
Yeah.
just wanted to like one other. I wanted to keep this
Yeah.
word. So this is probably Milne's work.
Yeah.
So if you work over a finite field, then a big result is that in that case, the category of motives, I guess we're thinking of it like as a Tanakian category or something, is generated by Artin motives and motives of abelian varieties. So that's that's not supposed to be obvious at all, I think, because abelian varieties are so much more manageable than arbitrary varieties. So it's sort of an amazing.
Okay, so you said that was Milne's thing, and you said that it was that notation refers to using the numerical equivalent.
Yep.
Okay.
So that's the one that gives you a Tanakian.
Yes. Yes.
So he has a paper, which is this 22 here, which
Uh-huh.
pretty readable, where he says that like experts sort of knew a bunch of this stuff about numerical motives over finite fields, but it's hard to find. So he wanted to like just explain it all really well. So he sort of analyzed. So that's a case that I've been trying to learn about because it seems like it's not so hard.
This vaguely makes me want to understand correspondences between abelian varieties. But anyway, I mean, that's something I know I'm supposed to learn about anyway. But anyway, go ahead, yeah?
Yeah. So then you can get an explicit description of the motivic Galois group. If I look at this carefully, see this is the connected component of the multiplicative of the zero there means the connected component of the motivic Galois group.
Yeah.
And I'm not even ready to talk about this too much, but once I told you that like the Vect conjectures said that when you count the number of points on a variety, say you have a variety defined over F field with P elements, and then you want to count its points over the field with P to the N elements. There's this formula, which is the so-called Riemann hypothesis for finite fields, but it's a formula for the number of points.
Yeah.
It's a sum of terms, and these terms are like some numbers to the N, where N is.
Yes. Yeah.
And those numbers are called Vect numbers.
Right.
They have properties, some of which we talked about, like algebraic integers, and their absolute value is known. So anyway, once I think you and I were like starting to get into that a little bit. So those are like the key. Those numbers turn out to be the key to understanding this motivic Galois group in this case.
Well, so I mean, again, just going the hyper simplified idea was that the terms are the things that sort of give rise to the motives or something like that.
Yeah, I think I'm a little confused about it.
Is
The way
that
it
right?
works,
Am I saying that
it's
right?
almost right. Yeah, it's almost right. The thing I'm confused about is that
I mean, the zeros of the zeta function,
both the zeros and the poles of the zeta function,
yeah,
of this zeta function, this is kind of zeta function has zeros and poles.
yeah,
And the zeros come from like the even dimensional cohomology of your variety, and the poles come from the odd dimensional cohomology,
yeah.
and the locations of them are like some encoding of these Vey numbers. And I prefer just thinking about the number of points on the, on the algebraic variety most of the time, and because then the number of points is just the sum with plus or minus signs of these Vey numbers to the nth power.
All right, I'll have to think about that later, but okay, but go ahead, yeah.
Yeah, so these Vey numbers often come in bunches that are Galois conjugates of each other. And something that I think I once understood, but I need to re-understand, is I was like looking at some really simple elliptic curves.
Yeah,
And there and working out everything in detail in that case, and I get like two Vey numbers that are Galois. The first cohomology of the elliptic curve is sort of where the exciting stuff happens. Because the
yes,
zero cohomology just gives you, it's like corresponds to a point. And the second cohomology gives you something also that's very bland. And the first cohomology, like the
yes,
two more Vey numbers that depend on the elliptic curve. And I was looking at some examples over the field with two elements,
yes,
and I was having trouble figuring out whether those two Vey numbers for that, whether they correspond to two separate one-dimensional motives, or whether they're like, it's just a single motive.
yes. And now it sounds like you're almost saying that it is a single one, but I don't know, but go ahead, yeah.
I have this feeling that it depends on the elliptic curve, but I'm very confused about that. So like sometimes those two numbers would be something like, sorry, I'm getting confused. It seemed to me that like sometimes those numbers would be Galois conjugates of each other, but if you just like put one into the rational numbers, you wouldn't get the other one automatically. Like let's see, we've been talking about stuff that like this.
Yes, yes.
That's why I'm sort of, this is a big digression right now. But then to other times,
yes,
like in the main example I was thinking of,
yes.
they were like 1 plus I and 1 minus I or something like that.
So I guess you just said, right? It sounds like you just said that they might be non-abelian things or something like that. That, you know, they're Galois conjugate, but you don't get the other one from, or something like that. It's related somehow, but yeah, go ahead. Yeah,
so I have this feeling, I want to straighten this out in my mind because I have some contradictory thoughts in my brain. But one line of thinking says that, like, depending on the nature of your elliptic curve, you will get into one or the other of these situations, and the word, I'm confused because some of the buzzwords that seem to be relevant. One is like complex multiplication for elliptic curves, whether or not it's that. But then there's like another one which seems to be relevant, which is whether your elliptic curve is super singular.
I don't even remember what that one means, but I know what the complex multiplication is like. But go ahead.
Super singular is it's like having quaternionic multiplication, And it's only like a thing for finite fields. It's like an extra amount of symmetry that elliptic curves can have in this finite field case. So
Okay.
anyway, I'm basically I'm done here. I'm sort of starting to veer off into other things. So I just sort of wanted to say that they're like these different quotients of motivic Galois groups that are sort of worth looking at.
Yes.
And I think just like the fact that when everything is working as hoped for, that the category of motives is the category of representations of some group, that gives me more of a flavor of like what motives are supposed to be like in the first place. So they're like the representations of Galois group, but then like representations of some kind of higher dimensional symmetries symmetries of the thing of varieties.
Okay.
Anyway,
again, yeah.
I'll stop there. I'll probably talk about this more some other time when I
Sure.
some more stuff.
Should we try to turn off the recording now, just so I can, try to get the next segment to work?
Okie doke. Yep. Let me pause this. Okay, so.
Okay. So, what I'm going to be talking about is presumably really related to what you were talking about, but I suspect it's at a way more elementary level. But so there's a paper that I've mentioned before. It's actually a pair of papers. One was a response to the other, a sort of allegedly nasty response to the first one. So the first paper is by B.F. Wyman, and it's called something like "What is a Reciprocity Law?"
Mm-hmm.
And what is a reciprocity law? And the paper that was a response to that was by Emma Lamer. And you can tell it's a response to that because they explicitly kind of mention in Emma Lamer's paper. But it was sort of a response to Wyman's paper. And I think Emma Lamer's paper might be called something like Rational Reciprocity Laws. And I think when we've talked about, we've mentioned these two papers before.
Yep.
And what's that?
I forget.
Yeah.
What the nasty response was, but that's a great way to get people's attention to say some paper is nasty.
Well, right. I mean, I'm as usual. Exaggerating or something like that. It was very politely nasty or something like that. But I heard from people who were sort of halfway involved in the situation that it was intended to be politely nasty or something like that. But and my attitude towards this saga of the Wyman versus Lamer, and then there's a bunch of other people who are sort of at least peripherally involved in this saga, and perhaps it starts with Schirmer, who perhaps motivated Wyman's paper. And then, so in a way, Lamer might really be replying to Schirmer in a way, compared to Wyman. Well, anyway, it's a complicated story. There's a lot of interesting peripheral characters. But so there's this sort of saga. And my attitude towards this has always previously has more or less been that Wyman is one of my heroes for writing this paper and for writing it in such a way that it was really accessible to non-experts. And so my interpretation of the reply to the paper by Lamer has sort of been that, well, Lamer was one of the experts and was unhappy about
Technical detail.
what?
Some technical stuff.
No, my interpretation. I'm much nastier. So
Just
I
give-
thought of it as, they were sort of angered at giving the secrets away or something like that. How experts sometimes get or something like that. But it turns out, I think the situation is much more interesting. That it turns out that both of these papers are in their own way very interesting, and there's much more in both of the papers than I had realized previously. And so, yeah, it's possible I'll bring up one or both of these papers. I mean, bring them up on the screen or something like that at some point. But I guess I'll wait to do that until the allegedly appropriate point in the discussion. So let me try to proceed here. And right, this is the point where I struggle to draw some pictures that I should have prepared much better beforehand. And particularly since these are pictures that I sort of often draw, you'd think by now I would have them prepared. So I don't have to draw them again each time, but I didn't quite manage that this time. So what am I trying to say? I'm trying to say that there's this picture that I sometimes draw of a Galois correspondence for some cyclotomic number field. And so sometimes I do it with the 20th cyclotomic number field, but recently I've been doing it with the 63rd cyclotomic number field, or perhaps also recently I've been fooling around with, maybe not showing it to you much, but the 91st cyclotomic number fields. And the Galois correspondences for their subfields. And where I'm getting these numbers 63 and 91 from is, well, so 91 is equal to what? 91 is equal to 7 times 13?
I guess so.
And
Yes.
63 is equal to 7 times 9. And so these numbers 63 and 91 are engineered. They're designed to involve a lot of cubic extensions, cubic field extensions. I mean, it has to do with the fact that 7 and 13 are primes, and they're equal to 1 mod 6. And 9 is not equal to 1 mod 6, but it's a very special number related to 3 cubic stuff or something like that. So right. So I guess so one, okay, I'm going to draw a slightly simplified version of one of the Galois correspondences that I've been drawing. I guess I'll sort of draw the one for the 63rd cyclotomic field, but it's not going to be the whole Galois correspondence. It's going to be a part of it. So let me try to draw it. Can I get this to work? So that's basically what it's going to look like. So these are going to be,
Sorry, what's this thing? Sorry, I blanked out.
okay, this is going to be some of the subfields of this 63rd cyclotomic field. So this 63rd cyclotomic field, if you count the total number of subfields it turns out it has 30 subfields. I'm only drawing 6 of them. And in fact, these 6 are all of the subfields of a certain subfield of the 63rd cyclotomic field. And I think the last time I drew this, I drew like 12 of them. But this is even simpler than that. This is only half of those 12. And in fact, this is really focusing on the cubic extensions. So let me see if I can sort of indicate what's going on here. So let me draw try this. I'm drawing that right. How does this work? It's like 4, 4, 4. Oh, but maybe I should really make this a 6 by 6 thing. Okay, and I'm going to have one axis for 3 squared, which is equal to 9, and one axis for 7. And the axis for 3 squared is going to have the numbers relatively prime to 9. So it's like, but listed in some funny order. It's like 1, 2, 4, 5, and 7, 8, but listed in the order of, I guess, all the we'll list them as powers of 2 modulo 9 or something. So it's like 1, 2, 4, 8, and then I think it's 7 and 5 or something like that. And the powers of 3 mod 7, right? It just so happens that 3 is a good primitive generator or whatever they call it, modulo 7, whereas 2 happens to be a good primitive generator modulo 9. Maybe that's what they call it, a primitive generator or something like that. So this would be 3 is good primitive generator. So it's like 1, 3. Are these the correct powers of 2 modulo 7? 1, 3, 2, 6. Did I say the powers of 3? Powers of 3 mod 7. 6 times 3 is 18, which is really the same as 4. And then I think the next one is 5 or something like that. Right. So this is these 36 numbers, you can think of that as being a sort of picture of GL1 Z mod 63. And and one axis is actually GL1 Z mod 9, and the other axis is GL1 Z mod comma Z mod 7. And the Chinese remainder theorem kind of says that they fit together like this. Some version of the Chinese remainder theorem says something like that. And since a Galois correspondence gives a correspondence between subgroups and subfields, so we're interested in subgroups of this group, and I can just depict them by, like, for example, that's a subgroup right there. That's a 4-element subgroup. Which, let's see, so that should correspond by the sort of upside downness, the contravariance of the Galois correspondence, that should correspond to a 9-dimensional extension of the rationals, because 4 times 9 is 36, right? There's kind of like it's a sort of inverse relationship between the size of the Galois group and the degree of the extension in this abelian case. That's making sense. Yep. So in fact, I'm only going to be interested in subgroups of this 9-dimensional field.
Subgroups of this 9-dimensional field.
Subfields, thank you. subfields of this 9-dimensional field, corresponding to what? Corresponding to subgroups that contain this 4-element thing.
Okay, yeah.
So that means that I can depict the subgroups that contain the 4-element thing just by drawing them, by drawing 1/4 of them like this.
And drawing the extra elements.
Yeah, the extra elements are just right by symmetry, right? So it's like 1 and 8 are really bunching together, and 2 and 7 are bunching together, and 4 and 5 are bunching together on that axis.
Yep.
Whereas on the vertical axis, the 1 and the 6 are bunching together, and the 3 and the 4 are bunching together, and the 2 and the 5 are bunching together. And I guess the way this bunching together is taking place is that we're saying that multiplying by -1 in this multiplicative group doesn't make a difference that we consider to be important in this context. And that has something to do with the fact that we're really trying to focus on cubic extensions and ignore the quadratic extensions that sort of intrude in here. So let's see, the Galois correspondence is upside down. So I should have the small subgroup at the top, big subgroup at the bottom. And then, in the middle, we kind of have something like this. And I'm not trying to list these in any very sensible order, but it's something like, right, it should be like that. And maybe this one. And this one.
Similar to stuff you were drawing last time, but it's not clear to me that it's really the same stuff. You were drawing a 3x3 square and various subgroups of it. And like the cool one was the third one in that.
Okay. Can I think about that? Let's see. Is that how much of a complete coincidence is that? Let me think about that for a second. That's a very important point. I have a feeling that is almost a complete coincidence. And that this is now showing. So that means that I'm very glad that you pointed out that it's a complete coincidence. I mean, unless I'm screwing up.
Yeah, you had Z-mod 3.
I mean, it's not a complete coincidence, but it's showing up for a different reason here. It's showing up for a different reason here. I'll have to think about what that reason is. But you're absolutely right that very similar pictures are showing up, but I really think they're showing up for a different reason here. So this is more like, I don't know, maybe from 2 weeks ago or something like that, where I had this Galois correspondence.
Yeah, no, you had that too. Yeah.
Yeah.
Okay.
I mean, one of the things that's going on here is that we can think of this little subgroup lattice that we've drawn. We can actually just think of it as the lattice of linear subspaces of a vector space over the 3-element field. I mean, just because it works out that way. We're dealing with an abelian group, which, right, an abelian group which happens to be the Cartesian square of Z mod 3. So its subgroup lattice is really just the lattice of vector subspaces, linear subspaces of this 2-dimensional vector space over the 3-element field. And that, right, I mean, that makes the picture make a little bit of sense, right? I mean, we've got a 2-dimensional vector space. It makes sense that there's, only one 2-dimensional subspace at the top. I guess right. I guess the 2-dimensional subspace is at the bottom, right? Yep. 2-dimensional subspace is at the bottom, the 0-dimensional subspace is at the top, and the 1-dimensional subspaces, which are the main ones of interest, are in the middle, and there's 4 of them, right? Because we're used to the idea that the projective line over a finite field contains one more element than the field. It's basically got this, point at infinity.
Yep.
Which one counts as the point of infinity is probably the one, either the one on the very left or the one on the very right, depending on how you arrange things or something like that.
Yep. Yeah, that all makes sense to me, including the one man's zero is the other man's infinity.
Yes, that's right. And so, but now what we're going to do, and it's eventually going to make sense, is we're going to sort of undo the sort of projectivization that we've done here. Like this, right? We say that this middle row here is sort of like the projective space of this two-dimensional vector space. But it turns out that the vector space itself, before you projectivize, is very interesting. So I'm going to draw a picture of that. And and once again, the picture really should be completely pre-drawn, but I'm going to try to draw it on the fly here without wasting too much time. So it's going to look something like this. Right. So there's something funny going here. I'm drawing a little 3x3 grid of even littler 3x3 grids. And that's not a coincidence. So what am I trying to say here? So what I'm going to think of these. How am I thinking of this? Well, look, let me try to draw some of it and then maybe try to figure out what the picture means. So I'm going to say something like, I'm going to say 1a squared and 1. Okay, this is going to be 1. No, sorry, I didn't quite do that right. Let me try to fix my mistakes as I'm going along. Okay, this is going to be all ones. And this is going to be kind of where the origin of the vector space is. For some strange reason. Maybe because I'm using some funny connection or something like that. Funny convention. Next one's going to be 1a squared and 1, and then 1a squared a 1. This is going to be 1a squared and 1. This is going to be 1a squared a and 1. Is this legible?
It's just barely legible, but it is legible. Just.
But maybe we do have a thing for that. We can change the size to make it in more legible. Maybe I'll just try to do that right now. Is there a thing here?
That looks good.
Let's try that. All right. Now, how do I get this to work? I think it's there. Okay, and I just have to use this a little bit. Okay, let's hope this is gonna work. And this is keep going.
I spaced out for a while and I don't know what these A's are supposed to be about.
Yeah, well, no, you might not have spaced out that much. I mean, I may not have said very well what the A's are. The A
okay, well.
So well, A is just some strange formal variable that I'm introducing. What it really is, it's going to be the generator of a 3-element abelian group. So this is all, powers of this 3-element, powers of this element A of order 3, that generates its own little 3-element abelian group. So it's like, so how does this one work? This one should be something like 1a squared on that axis and 1a squared on that axis. So I mean, this one in the upper left-hand corner, that's, I guess what I'm doing is I'm drawing like the dual vector space. Right, so there's a vector space whose with one of these two-dimensional vector spaces over Z mod 3, where the vectors are simply the 9 squares in the grid. 9 squares in one of these small grids. But then to give a linear functional on that two-dimensional vector space is to fill in the values of a homomorphism. You fill that grid in with with values that give a homomorphism to this 3-element abelian group, which for some reason, instead of calling the 3 elements 0 and 1 and 2, for some strange reason, I'm calling them 1, a, and a squared. And so this is like the 0 linear functional, but drawn in this funny multiplicative notation.
Okay.
And
so yeah, you don't even need to write in all that stuff, right? That is, it's
right. But like, let me just put in one of these in the middle for me to get a sense of what it looks like. So I think it looks like this.
Which looks sort of like, for some reason, you've gotten me sensitized to this sort of funny Knight's move.
Yes.
thing.
Yes. So, I mean, let me just put a very tendentious squiggly arrow here, suggesting that the squiggliness is supposed to mean that in some very informal sense, the picture on the right-hand side is a sort of coarsening of the picture on the left-hand side.
We're keeping track of what equals 1, the kernel.
Yes, that's exactly right. Right. So this is sort of a kernel. But I'm putting it in quotation marks because this squiggly arrow is in some sense depicting the kernel process. So let's see. So how does this work? I mean, we've got 9 vectors over on the left, and we have 6 subspaces over on the right. So I think, yeah, it looks to me like there's this one in the upper left-hand corner. That's the only one whose kernel is everything, I guess.
And you'll never get one whose kernel is just 0. So the one on top never gets.
That's right. So right. So yes, that's right. So the 0 vector has this kernel down at the bottom here. All the others have a one-dimensional kernel, and there's doubling up. Right, that there are 2 that have this kernel. Where are the 2 that have this kernel? Can we find them? Let's see. I guess they're these 2 right here. Let me try to.
Yep.
Is that right? These 2 right here.
Yep.
Are the ones that end up over here.
Yep.
And these 2 over here are the ones that end up over here. Et cetera, et cetera, et cetera. Well, I think it's actually right. I think it actually ends up being weird. Is that right? That
well, it's by symmetry that one and the other diagonal one. Yeah, those have to.
Yeah, but I think they end up going to the one that I didn't expect. I think they end up going to this one over here or something like that, right? Right. You can see, as you say, there's this night move.
I was telling you that.
Oh, that's what you were telling me.
Yeah, I was saying that, like, yeah. with that before I even knew it. Right as I said, hey, this night move pattern, which was so crucial last time for.
Aha.
for
Oh,
interest.
I see what you said. Okay.
It's
Okay.
showing up here for
Oh, that sensitization. Okay. Yeah. Again,
sillier reasons. This
again,
is
you're blending together these two
Yeah.
things that I'm claiming are completely unrelated.
they are, yeah. So
But-
last time the diagonal symmetry, the flipping across the main diagonal symmetry of the square was like a profound and important thing. Whereas here, I think it's like a completely irrelevant thing because those are like the 7 and the 9 axes, and so there's
Yeah, but it's hard to be sure that there isn't some secret thing going on here. But yes, we have mysterious coincidences going on here, which maybe are just coincidences. But so the thing that I'm sort of halfway understanding now is that this picture over on the right-hand side, this, remember, is a picture of a Galois correspondence. And there's this sort of refinement, right? The picture on the left is a sort of refinement of the Galois correspondence because it's got more information in it, right?
Mhm.
I mean, what do we mean when we say, I mean, you could make various ways to make sense of what do we mean when we say it's got more information. But basically, you know, for one of these things in the middle row, there's an extra bit of information, an extra sign bit of information. It's like an extra orientation bit of information over in the picture on the right. And this is also connected, right? This is connected with the fact that the multiplicative group of the 3-element field has a 2-element the two, did I say that backward? The 3-element field has a 2-element multiplicative group. So, you know, giving this sort of orientation information on a 3-element set is this extra single bit of information that's showing up here.
Mhm.
And right. And why is this showing up? This is showing up because over on the right-hand side, this Galois correspondence, especially the things in the middle row, are cubic extension fields. Whereas the things over on the left are Z mod 3 torsors. So, right, in some sense, the group that's active in the middle row on the right is 3 bang. Whereas the group that's sort of active in the picture on the left is Z mod 3. And so there's that, you know, extra orientation bit of information that's sort of, in some sense, giving us the difference between the coarser picture on the right and the finer picture on the left. And so what I think is going on here, and this is coming from my interpretation now of things that I read decades ago in Wyman's paper. There were certain mysterious things, I liked Wyman's paper so much because it was so easy to understand. But even though it was so easy to understand, there were still some mysterious things in it that I didn't quite catch. Whereas now I think I'm really seeing that there's something very interesting that Wyman vaguely refers to, and it really has to do with the extra information in the picture on the left compared to the picture on the right. And the picture on the right is a Galois correspondence. Picture over here is a Galois correspondence. The picture on the left is something a little bit different. I don't think you could exactly refer to it as a Galois correspondence, but it's a whole, what I think it is the sort of, what I'm guessing it is, it's the cohomological picture of the Artin reciprocity theorem. So this is the point where we should try to find some sort of, let's try to find Wyman's paper online. I'm hoping it's really easy to find B.F. Wyman's paper online here. So can you Google it? I'll try to Google it, see if we can find it here. B.F. Wyman.
B.F.
B.F. Wyman.
Yep.
and it's called like what is a reciprocity law or something like that. Did you manage to find it yet?
Almost.
So yeah, it's showing up here. How do I get it? Is this gonna show up? Click on it. And did you bring it up yet?
Yeah, I've got it. Maybe I should.
Yeah, it might be easier for you to show it. Like maybe you just grab the screen for a second.
Yeah, I'll grab control of the
Yeah.
console.
Yes.
Then I have to.
Yes.
Then I have. So here it is.
Okay. Okay. That's pretty much right at the beginning, but just to prove to me that it's the beginning, could you sort of scroll a little bit?
What is it?
It's hard to. I just want to see that, you know, I don't want to see the JSTOR stuff. I just want to see where it says the title. What is a reciprocity law? That looks good. All right. So let me try to read a little bit of this out loud, because so in fact, I mean, right at the beginning, right at the, you know, the very first 2 or 3 paragraphs of this paper is the part that seemed mysterious to me when I read this the first time. Or did it seem mysterious to me? It might have just gone right past me without my even understanding it or noticing. Whereas all the rest of the paper was stuff that I found really interesting and accessible. Whereas now, you know, I'm suddenly noticing that these first 3 paragraphs of this paper might be telling me something very interesting. So let me try to read these first 3 paragraphs out loud. So what is a reciprocity law? Introduction. The law of quadratic reciprocity has fascinated mathematicians for over 300 years, and its generalizations and analogs occupy a central place in number theory today. Fermat's glimmerings and Gauss's proof have been distilled to an amazing abstract edifice called class field theory. And then it says, as a graduate student, I learned the great cohomological machine and studied Artin's reciprocity law, one form of which gives an isomorphism between 2 cohomology groups. And that's it actually right there. That's what I think we're sort of seeing here. I think that this picture that I was drawing, that I'll go back to in a moment when I re-grab the screen, I think what you're going to see once again on the screen is, I'm hoping that it's something practically exactly like this thing that that Wyman is referring to here, a form of Artin's reciprocity law, which can be thought of as an isomorphism between 2 cohomology groups. So, I mean, again, when we go back to the picture, you'll remember that I have, you know, a thing on the left and a thing on the right. The thing on the right is a subgroup lattice, and it's a picture of a Galois correspondence. Whereas the thing on the left is not a subgroup lattice, it's a 2-dimensional vector space. But that 2-dimensional vector space is the thing that I think we're going to be interpreting as a cohomology group. So, you know, that's kind of what's going on here. That's one of my current big guesses, my current big theories about what's going on here. That one of the things we're doing by taking the Torsor viewpoint towards this Galois correspondence and taking the Torsor viewpoint, in this case, Z mod 3 Torsor, taking the Torsor viewpoint towards these reciprocity laws, the Artin reciprocity law and so forth. By taking the Torsor viewpoint over this, we are putting this in a form that people very well may express in terms of cohomology groups. And for me, back when I was, you know, first reading Wyman's paper, the fact that he mostly avoided the cohomology groups, that was a big feature. You know, to me, cohomology group was just like this obscurantist terminology, which I really very rarely wanted to hear about. I always wanted to try to give it, if somebody talked about cohomology groups, I always wanted to try to rephrase it somehow and turn it into something else having to do with category theory. Like secretly some monodal categories or something like that, or perhaps monodal groupoids or something like that. And of course, that's something that you and I want to do here. So, right, we're not just settling for, it's not like I want to settle for an expression of Artin's reciprocity law that is expressed in terms of cohomology groups, but rather, we want to, we meaning I'm saying that you and I want this. We want to use what we know about the relationship between cohomology and category theory to, that's going to be giving us the tools we need and the hints we need in order to interpret the Artin reciprocity law, in order to reinterpret it from being something about cohomology groups to being something about something that you and I like, which is some sort of monodal categories or something like that. Well, I mean, and perhaps into something that I've been referring to lately as being this Tanakian viewpoint about Galois theory and reciprocity laws. But Tanakian means it has to do with nice monodal categories of some kind, nice tensor categories of some kind. Understanding a group in terms of a Tanakian-like category of representations of that group.
Mm-hmm.
So that's kind of where we're going here. But let me before we leave this and go back to the pictures, let me just make a few minor comments about the rest of the first three paragraphs of Wyman's paper here. So right after the part that I just read, which is the key part for us, he says, a little late, well, okay, right. I mean, he has just said, and I've just emphasized that he says that Artin's reciprocity law can be expressed as an isomorphism between two cohomology groups. And then he says, a little later, I read Shimura's paper called A Non-Solvable Reciprocity Law and couldn't understand the title at all. Where were the cohomology groups? Why was Shimura's theorem a reciprocity law? And then he says, it was an embarrassing but healthy ignorance because it made me go back and figure out the number theory that lay behind all those cohomology groups. And basically, I think that's, he's describing how this paper that he wrote resulted from, his failure to understand what Shimura was saying led to him struggling to understand it and then to explain it to other people in this paper that he wrote. And okay, and then let's read the rest of the first three paragraphs. So he says, made me go back and figure out the number theory that lay behind all those cohomology groups. Such a reassessment is especially important nowadays because it seems more and more certain that the next generalization of the law of quadratic reciprocity will require new techniques, and nobody is quite sure which techniques will work. So I think he's vaguely alluding there to things like the Langlands program, which are sometimes thought of as giving a non-abelian reciprocity law, but in some very generalized sense of reciprocity law, and generalized in the same way that Shimura was really generalizing the concept of reciprocity law. And of course, Shimura is very, well, I say of course as though I actually understand it, but Shimura's work is tied in with the Langlands program in some very interesting ways. But in particular, when Shimura's paper called A Non-Solvable Reciprocity Law, that's already right. That's again tying in with the idea that the Langlands program is about something like non-abelian reciprocity laws, because non-solvable is a kind of non-abelianness, and you know, having. Actually, I guess it's actually a very serious kind of non-abelianness. I mean, it's right. Even when you get to non-abelian and having something be solvable, that's a very mild form of non-abelianness. But I guess I hadn't noticed that Shimura was actually getting not only past the point of abelianness, but he's getting past the point of solvability, I guess. I'm not sure I noticed that. So like I say, Wyman wrote this paper, and then he got this response to this paper from this expert, Emma Lamer. And I think from what I've heard, and again, I've maybe been getting information from the wrong people about this, but from what I've heard, Lamer's response to the paper was sort of based in part on, you know, they may have thought that Wyman was being sort of pro-cohomology. My interpretation of Wyman's paper has always been precisely that he was, you know, being anti-cohomology, that he was explaining things in a much more concrete way than, you know, sometimes the tendency happens to be when people express things in terms of cohomology. So, you know, I almost thought that Lamer misinterpreted what Wyman was doing. But it turns out that regardless of whether Lamer was misinterpreting Wyman's paper or not, what Lamer's paper is doing is also a very interesting thing. And it took me a long time to realize that, but the key clue to that is, I guess, in trying to understand what the title of Lamer's paper means. So the title of Lamer's paper is something like, I think, rational reciprocity laws or something like that. And I don't think I had any idea what that meant. You know, what is a rational reciprocity law? But I think what's going on there is simply that, you know, it's the idea is the reciprocity law is sort of the base field. When you have a reciprocity law, roughly speaking, you can ask what is the base field over which the reciprocity law is dealing with. And you know, in traditional cubic reciprocity, in some sense, the base field that you're working over is the Eisenstein field, or in traditional quartic reciprocity, in some sense, the base field you're working over is the Gaussian field. Now, there are different ways of interpreting it, but that's roughly the way the situation is. So that when you ask, as Lamer is asking for, when you ask for a rational reciprocity law, you're saying, let's try to back up a little bit. Let's try to do this more difficult, possibly more difficult task of describing the reciprocity patterns, starting, you know, not using the Eisenstein field or the Gaussian field as a crutch, but instead going back and trying to give the splitting patterns, the reciprocity laws that actually would apply starting from the rational field itself without the help of these helper fields. And that's interesting for all sorts of reasons. One reason it's interesting is because I've actually been trying that sort of thing myself, right? I've been sort of saying, well, from this Tanakian viewpoint, we're going to try to understand Z mod 3 torsos and try to understand them not over the Eisenstein field where they become very trivial because the group just splits over that field, but let's try to understand the Z mod 3 torsos over the rational field where the group does not split, and so the representation theory is more interesting in some way, more non-trivial, more interesting. So now it's almost like I'm trying to suggest that there's some connection between Lamer's viewpoint and my viewpoint. And maybe there is, but it's also a little bit tricky because there are different interpretations of what you could mean by going back to and working over the rationals as a base field. I mean, it sort of has to do with the fact that, you know, as you recall, in last week's discussion, I was talking about how there were these two different degenerate orbits. Right? That's what you were sort of pointing out to. There was this diagonal orbit, and then there's this funny night move off diagonal orbit. And those were two different orbits, and one of them was relevant to cubic reciprocity in a certain way, but one of them was relevant to cubic reciprocity in a slightly different way. So there are different interpretations that you could give. So I'm not claiming that what Lamer was doing and what I was doing were exactly the same, but there are very interesting relationships because of this philosophy of going back to the rational field and starting from the rational field instead of using these helper fields as helpers. But on the other hand, Lamer's paper is very interesting for yet another reason. I mean, it's connected with the way that Lamer goes back to the rational field. So, like I say, the way Lamer does it, by going back to the rational field, but looking for the patterns, for the reciprocity patterns for like cube roots or fourth roots or something like that, Lamer is making the problem more difficult. And of course, making the problem more difficult in a good way, that it's, a more interesting problem to try to solve. And in fact, if I understand correctly, if I'm not screwing up too badly, what Lamer is actually doing in that way is actually making some of these reciprocity law problems into non-abelian reciprocity law problems. Because, you sort of have to go, the first step is an abelian step from the rational field to the helper field, like the Eisenstein field, for example. And then the second step is another abelian step from the Eisenstein field to some cube root extension of it, some cubic extension given by adjoining a cube root. And
that
so
makes Shimura's title even more
interesting.
He's saying
that's right.
Better than that.
That's right. But right, part of what I'm saying is that already what Lamer is doing is interesting because it has two abelian steps which do not combine in an abelian way, but instead they combine in a solvable way. And then it seems clear that I shouldn't say it seems clear. And then my vague impression is that part of what Lamer is doing is showing that these kind of solvable reciprocity laws actually do have a history, a pretty long classical history, which may have in some way inspired the Langlands program, inspired Shimura's work. That, so there are these solvable reciprocity laws that apparently go back to people like Jacobi and Gauss, but they actually in some way seem to sort of anticipate the Langlands program. Don't trust me to have gotten that correct, but that's my vague impression about what's going on. So, okay, I can't quite see what time it is. What time is it here?
It's 10 to 1. It's late. One thing I have to mention,
go ahead.
You haven't at all in the last many months ever tried to state a reciprocity law that is actually connect the splitting patterns of primes to all the stuff that you've been talking about. So that's what's what I'm burning and I was hoping for today, and now it's because last time we came very close. We were just on the edge of doing that, and now we're still kind of just on the edge of doing that. Because you realize that you're drawing it out. I can take it, but it's a little tough to take.
So I mean, all right, I'm gonna, since I've already got the picture drawn here and we're short on time, we got part of the picture drawn here. I'm going to try to, in some very sloppy way, use this picture.
Sharing my screen and you start sharing yours.
Okay, so yes, I was forgetting that my screen isn't really showing. So yes, this is the picture that, again, I'm trying to connect to Wyman's discussion of the cohomological interpretation of the reciprocity laws. So, I mean, we should really take some stab at some point, not right now, but at some point, we should really try to express this in terms of, we should try to get explicit about what cohomology groups are involved here, and you know, what where is there an isomorphism of cohomology groups going on here?
Yeah, that's what I want to know. This all looks so much, this looks like, this picture just looks like you're looking at different vectors in a two-dimensional vector space, seeing what subspaces they span, and then mapping them to a lattice of subspaces, which
Yes.
sounds like too simple to be all that interesting. It's just, I mean, it doesn't sound like reciprocity laws anyway.
Well, but it really is. It really is.
That would be great. One second, then it would be good.
I mean, and it's connected with, right? It's sort of connected with this quadratic analog from which we started developing this cubic analog. So, right, I mean, there was the idea that the quadratic extensions of the rational numbers are, roughly speaking, classified by square-free integers or something like that. Which another way of saying that is we're taking what? We're taking GL1 of the rational field, and we're modding out by the squares. You know, in a sort of gauge fixed way, you can say that that's the same thing as the non-zero square-free integers or something like that. Maybe we could even count 0 as failing to be square-free or something like that. So the analog of that we're doing right now, I mean, so you just sort of implicitly or explicitly asked, where are we getting some, where in this reciprocity game are we getting some sort of vector space over the 3-element field? And so basically what we're doing is we're taking GL1 over the Eisenstein field, and we're modding out by the cubes. And that, right, that's a vector space over the 3-element field. Just in the same way that if we took, you know, GL1 over the rational field and mod out by the squares, that's giving us an infinite dimensional vector space over the 2-element field.
Seems like somehow the 2-element group is getting promoted to a field there in some sneaky way.
It is happening in some sneaky way, yes. Right, maybe I should have thought about that more, but I mean, it I mean,
GL1 Eisensteins or GL1 rationals, and you mod it out by a subgroup, and then you're saying that that's a vector space over.
Yeah, well, I mean, right, modding out by the cubes is the same thing as saying take this abelian group and tensor it with the field of size 3. Right? If you take an abelian group and you mod out by the cubes in it, all you're doing is you're saying take this abelian group and tensor with the field of 3 elements so that it is now a vector space over the field with 3 elements.
When you're saying tensor it with the field, do you mean, I don't know much about tensoring a group with a field.
Tensoring an abelian group. Yes, you do know about that, right? You can tensor in a, right? You can, I think you know about this. I'm pretty sure you know about this.
Well, they're both as Z modules. Is that what you mean?
Yes, that's right. Both as Z modules.
Okay. But
We're
then,
tensoring.
yeah, okay. So I mean, that
So isn't there a name for that? What am I trying to say? Not restriction of scalars, but extension of scalars or something like that.
yeah, but extension in a very
Yes,
downward.
in this way that, right, it's the only thing that's really being extended is the property that everything is order 3. So what were you saying?
So if I take a abelian group and I tensor it over Z with a ring, I mean, I could define the tensor product, just forget it's a ring, just tensor it with another abelian group. And that's what you, but then, so what is the ringiness of the ring, or in this case, the field, do to the result? That is, I'm just still puzzled by why you took a group, an abelian group, and you tensored it with a, okay, you're going to call it tensoring with a field, and then you're getting a vector space over the.
I mean, like I say, it's extension of scalars from the ring Z to the ring Z mod 3.
Okay, yeah, sorry. Let's see. Yeah, okay, right. That. So you're taking a Z module and you're tensoring it with Z.
Tensoring it with an algebra of that ring, of the ring of integers. But an algebra of the ring of integers that's just a ring.
Okay. Okay, I'll still have to think about why you're getting a vector space over this.
Well, I mean, because vector space over a field is just a synonym for module over that underlying ring of that field. So, we just have, we have this ring homomorphism of commutative rings going from Z to Z mod 3. And they just happen to be very special rings. The Z is itself the initial commutative ring. And Z mod 3 is one of its finite quotients. And it's a field. So, yeah. So we're starting out with an abelian group. We're ending up with a vector space over a finite field. That's what extension of scalars.
Okay. Yep.
Works out to in this specific example of a homomorphism of commutative rings.
Okie doke. Yep.
And so, and this is right. This is about the same point where you made the joke about cube-free numbers or something like that. Although in this case, it should be cube-free Eisenstein numbers. Cube-free Eisenstein integers. That probably does actually turn out to be the same thing as this vector space that we're talking about. And so right before we quit, I'm going to try to pretend to do some examples here. And then next time we'll actually do these examples. So again, let me try to write down in a very sloppy way some of these Eisenstein primes. So there's like, these are the, right, I'm going to write down like some of the, I'm going to write down the prime factor, at least one of the prime factors of the Eisenstein prime, the Eisenstein non-prime 7 has Eisenstein prime factorization given by what? It's like 7 equals 1 plus 3 times. I hope I'm getting this right.
I think we've done this twice already.
Yes, and I realize now that one of the reasons I keep on having trouble getting the same answer from one time to the next is that you can get different looking answers that are actually the same because you've just multiplied by some, element of some Gaussian integer, some Eisensteinian integer that is itself invertible, right? So that doesn't change the primes that you're dealing with or something like that. So it's 1 plus 3 times 1 1/3 and 1 plus 3 times 1 to the 2/3. So I think that actually turns out to be correct or something like that. So this is going to correspond. So I think the way it's going to work out, this one right here, for example, is going to correspond to 1 plus 3 times 1 to the 1/3 times you know what? I thought I had so much freedom in here that, you know, that I could just pretend any one of them would correspond to any one of them would be correct. But I think there's actually probably enough information already in the data. I think I would probably need to say that this one, maybe this one over here. I think this one over here might correspond to 1 plus 3 times 1 to the 1/3 times 1 plus 3 times 1 to the 2/3. Sorry. Squared. sorry, I was having so much trouble with the pen there, and then what I'm saying is that taking the cube root of this number that's going to correspond to, well, if you sorry, the picture is getting very sloppy here right now, but you can see that this one is right. You follow this arrow, it's supposed to go over here.
Yeah.
And then this green arrow is supposed to go, where does it go? It goes over here. I'll have to check next time and see if I'm actually getting this right or getting it backwards or something like that. But what I'm trying to say here is that I'm trying to begin to actually carry out this project to identify which cube-free Eisenstein integers, so to speak, meaning, you know, these elements of this vector space that you get by taking GL1 of the Eisenstein integers, but then modding out by the cubes, in other words, by tensoring with the maybe that's sometimes, am I trying to say, no, never mind. I thought I was going to try and say something about torsion or something like that, but that's probably not the right word. Probably what the word we want is extension of scalars, like we've been saying. But so I'm trying to begin to carry out this project of identifying which of these cube-free Eisenstein integers, such as this one right here, this, if I did it correctly, is a cube-free Eisenstein integer. And taking its cube root is going to give us a torsor, and taking the cube root of the square of that is going to give us another torsor. And that's why we're going to get two different torsors right here. But they're going to correspond to the same cubic extension of the Eisenstein field. So we're pretty much out of time, but I'm going to, next time I'm going to have to try to clear all that up and make this picture make sense, but with very explicit numbers, so that, we're going to have 9 torsors over here, and we're going to try to say very explicitly how they correspond to, taking cube roots of specific Eisenstein integers, and how the reciprocity laws work. which will involve taking those torsors and pushing them forwards to the finite fields. And this will give us, I think, the isomorphism between cohomology groups that Wyman was talking about. But yeah, so I'm leaving this in a very unsatisfactory state, but I'm hoping you can get an idea of where we're going. That, you know, we had this Galois correspondence, but now we're incorporating this extra orientation bit into the Galois correspondence. So it's no longer going to be a Galois correspondence in the form of a lattice of subgroups. Instead, it's going to be this isomorphism between cohomology groups, if you like to think of it that way. But of course, you and I should actually try to think of it in a better way, which is from this Tanakian viewpoint.
Part is,
say that again?
You haven't said what the isomorphism part is. You've described.
I have actually said it in a very sloppy way. I mean, I said that the isomorphism part is actually just pushing forward the torsor, slightly reluctantly pushing forward the torsor from the field to from the number field to the finite field. But, you know, to make that really make sense, you should really think of it as a number ring, and then you're pushing forward to a finite field, because you actually have a ring homomorphism from the number ring to the finite field. But that involves getting slightly more explicit about ramification and how to deal with ramification than we've been dealing with so far. So as usual, I'm hoping you're getting some idea where we're going here, and I'll try to go further with it next time.
Yep.
Okay.
Okay.
Thanks a lot. I'll see you.
Yeah.
Okay.